measured decay envelope, and that was how we are able to obtain the damping coefficients. Can you go to the slide, please?
Okay, and the first question, phase of the interaction. Did you do any experiments at low frequency supply excitation? Low frequency.
The question statement asks us to use high frequency supplies, so I don't think low frequency supplies is relevant in this question.
So what do, in your model, you didn't have a range of the frequency. So your model has can it applied at the low frequency?
Now, to clarify, I do have a theory and a plot of amplitude against AC frequency. Can you go to the plot, please?
Well, in your theory, you didn't give a range of the frequency. So, do you think there is a range of frequency that will the pendulum can get an undamped oscillation? The range of the frequencies.
No, we can see that no matter the AC frequency in this case, stable amplitudes will always exist.
So let us assume that if the frequency of the AC supply is 10,000 hertz, so what will happen?
Now the thing is that at increased AC frequencies, the amount of energy gained per half cycle actually decreases.
Yes.
So for you to use such high frequency, you will need a very, very strong electromagnet.
Yes.
And that is not very feasible experimentally.
And you think that there will be many amplitudes that they can be stable?
Yes, exactly.
And as the hertz goes up, is there any possibility that the pendulum can be stable at any given amplitudes?
Now, that is theoretically possible at infinite AC frequency and infinite electromagnetic strength. And actually, a very interesting aspect of this is that if you extend that graph up to, say, 180 degrees amplitude, you will observe that these graphs curve so much that it becomes a continuum at 180 degrees amplitude. This is because at 180 degrees amplitude, the period of a pendulum approaches infinity. So actually, as we go up the amplitude graph, it goes from a discrete spectrum to a continuum spectrum.
Yes. And according to this graph, can you predict at low frequency what will happen?
Yes, you can see that we can extend the graph all the way to, say, 5 hertz, or even, this graph, you can see the domain is from 5 hertz to 80 hertz. So we are able to predict what happens at as low as 5 hertz. But this problem statement tells us to only investigate high frequency AC power supplies.
So I have noticed that your stable amplitude is over 90 degrees. So what's that explanation?
Now, the thing is that there is no physical...
Why the amplitudes can be up to more than 90 degrees?
90 degrees correspond to the fact that if our pendulum goes like this, we define the theta to be here. So our pendulum can actually swing up 90 degrees and even more. But this will require a very, very high strength electromagnet. There's no physical reason why the amplitude cannot go above 90 degrees.
I want to ask another thing, that is the current, the intensity of the current can influence this graph. Because if the current changes, the distribution of the curves will change too. Will it change?
Yes. Indeed, the stable amplitudes will change by a little bit. A graph will be shown soon. AC current graph, please. Yes, we have done some investigation on the effect of AC current. So we can see that as we increase AC current from 0.5 amperes to 2.5 amperes, our stable amplitudes remain roughly the same. However, if you zoom in very carefully into this graph, you will see that this constant trend is actually a linear trend, but with very, very shallow gradient. In fact, a 5-fold increase in AC current will only result in a 0.2% increase in stable amplitudes. This is very strong evidence that our negative feedback mechanism is indeed at work.
Okay, and another thing you mentioned about chaos in this non-linear system. Okay.
I mentioned the possibility of chaos.
Yes, you have mentioned the possibility of the chaos. So I want to discuss with you that how do you define that this nonlinear system is a chaos or is it not? Do you have any methods to...
As of now, given our data and our theory, we cannot give a concrete stand about whether there's chaos or not.
You have your dynamic equations for this nonlinear system, yes?
Yes, I do have that.
And do you aware of the Lyapunov exponent?
Yes.
And can you have any possibility to calculate the Lyapunov exponent?
Now, the thing is that the definition of chaos requires several conditions to be met.
Yes.
Not only sensitivity to initial conditions.
Yes, and I want another thing about the experiment details. Does every seat you release the pendulum can lead to an undamped oscillation.
Gentlemen, when you're adding to your diagram, can we clean up some of the things? It's getting very difficult to follow what you're doing on the...
So to clarify, your question was, if I release the pendulum multiple times, will it reach stable amplitudes every time?
Yes.
Is it?
Yes.
No, it will not. As shown by our color plot.
And I want to ask, is this sensitive to the initial condition?
It is sensitive to initial conditions, but that is not sufficient to gauge whether it's chaotic or not.
So do you believe that if you have when you release at this about 70 degrees and you release about 70.1 degrees, it will lead to a different result?
So this is the initial amplitude of release.
Yes.
It could reach different results.
So how does your so in your error analysis, how can you avoid that your experiment errors could not avoid these things? Because if you have a very small error, it will lead to a different result. So how does your control error to meet this?
So we have observed that actually the sensitivity is very great towards AC initial phase.
Yes, but we have in some region it's very.
But for the initial amplitude, we have observed that it's not that sensitive. The main sensitivity is to the AC initial phase. So you can see it's quite dense on this plot.
Yes.
Yes. So actually, this error that you spoke of, it's not that sensitive.
Yes. And another thing that I want to discuss you, I put earlier that the force, okay? You mentioned that force is like this graph.
Yes.
Yes. And I mentioned that if the solenoid is this way and the magnitude is this way.
Yes.
So this is tangential and horizontal, and your magnet is vertical one. So how does this one has the largest force?
So we can imagine our solenoid qualitatively as a bar magnet, and we have our magnet here. So we know that these two poles will attract each other, whereas these two poles will repel each other. So as this magnet swings by, it will experience this pair of attraction and repulsion. And that's why I can see on the screen there quite clearly that there will be a resultant force on a magnet.
Okay, it's very clear. And what's the discrepancy between your theory and the experiments? Because in your what's the assumption of your theory? Is this has no assumption? It's just a deduction of consider everything? So
our theory assumes that there is no back induction effect. So we have our solenoid and we have our bar magnet.
Yes, and have you ever considered that the Lenz's law that it will have an induction effect?
We did consider it, but we did verify that it's not that significant, so it's a very good approximation.
Can you do an experiment, but you didn't show that experiment? That will verify that there is no...
Yes, I didn't show the experiment because of the time limit, but in this case, we can verify that as our magnet swings across our solenoid, which is unpowered, the amount of voltage induced is very low. This is on the order of 0.06 volts, but the voltage we pass through our solenoid in our experiments is close to 30.
Remember, this is a non-linear system, so every small discrepancies can lead to a large thing, and you didn't conclude this to your theory part. Can that be a little...
No, let us first note that this voltage would result in the currents in our electromagnet. And we have previously shown that AC current, even if you vary AC current by a lot, you still see a almost constant trend for the stable amplitudes. So we have good reason to believe that this is not significant.
And about the nature of the various amplitudes, you just mathematically described this, it will happen, and what it will be. But the physical meaning, why does it lead to various amplitudes? So what does the various amplitudes refer to? Does this mean the interval time that it will get back to the equilibrium is different?
Of course, at different amplitudes, the time taken to go back to electromagnetic will be different.
So the very nature of the various amplitudes is because the interval time is different.
Yes, I previously shown the criteria that the period of the pendulum must be an odd multiple of the period of the AC source.
Yes, and as the frequency goes up, and you notice that because this, if we release as this one and this is T2, and we have time interval T1 and T2, and this minus this is about the period of the AC supply is T. Does this mean that this is a stable amplitude and this is a various amplitude? Is it correct?
I don't really get what
This is a stable
you...
one, and
okay.
this is the stable one, and
Okay.
this interval is T1, and this interval is T2, and this minus thing is equals to the T, and T is the period of the
Yeah, actually,
solenoid.
a multiple of T will also work.
Oh, yes, and
Yeah.
do you think this is correct?
It's roughly correct. It's an approximation.
roughly correct?
It's an approximation.
It's an approximation about what? What is your approximation?
Now, firstly, this assumes that as a pendulum swings into an interaction zone, it will interact
Yes.
over an infinitely small area. So actually, as the pendulum swings across our electromagnet, it will be continuously accelerated or decelerated, but that's not taken into account in this theory.
Yes, so you believe that this is the very nature of the
It
various
is an
amplitude.
approximation for qualitative understanding only.
And consider this has an acceleration or deceleration thing. Yes.
Yes, that's not accounted for in here.
And another thing is, no, that will be okay. Thank you.
Okay, thank you.
Okay, you go straight on to summarizing the discussion.
So the reporter answered this problem very well and considered a lot of things, but several things that he didn't consider and didn't explain is first the coefficient of the damping. This is a relevant parameter, but he didn't investigate it. And the very nature of the various amplitude, he agreed with me, and about the induction effect, he doesn't conclude it into his theory. So I believe that it will cause some errors in this theoretical analysis. And his other works is done very well, and gave a very direct version of this problem, but I think these things will be correct. And also, we believe that at the low frequency to the high frequency, there must be some change or some relationship, but the reporter doesn't conclude this one and investigates this one, and I believe that it is very crucial. Thank you.
Okay, thank you. Can we have both the opponent and the reporter on the stage for questions from the review?
Welcome, ladies and gentlemen. I'm Fredrik Grabowski from Team Poland, and I'd like to ask a few questions. First, to the reporter. How accurately did you measure the period of the pendulum you used?
We do not need to measure the period of the pendulum. We only need the mass of the pendulum and the damping coefficients that we plug into our equation of motion.
Okay. How accurate was this measurement?
The mass of the pendulum was taken to four decimal places using a precise
Thank you very much.
balance.
Could you go to slide 83, please? And while you're doing this, I have a question for the opponent. What parameters do you think are important in this phenomenon?
The amplitude of the current and the frequency of the current and the pendulum's length, also the period of the pendulum and the coefficient of damping.
Okay, thank you very much. So, to the reporter, here you have for the frequency of 80 Hertz, you have very, very dense, discrete amplitudes. Did you observe this in your experimental setup?
As I've explained, if you were to reach these high amplitudes, you would need a very, very powerful electromagnet. But it's not feasible to do so experimentally because our electromagnet will overheat if you pass too much current through it.
Okay, thank you very much. And the opponent mentioned some key parameters. Which of those parameters did you vary in your experiments?
Fitted parameters, is there?
No, what parameters did you vary in your experiments?
We varied AC frequency, AC initial phase, pendulum length.
Okay, for one frequency of the AC power source, how many experiments did you carry out?
You can see clearly the amount of data points on my plot. So, can you go to AC frequency graph, please? Yeah, so every point
10,
of those
20 experiments?
Every point of those graphs is an experimental run.
Okay. Okay, so for 20 there were 2 amplitudes, 2 experiments.
No, so we did experiments. So we did experiments until we can observe all of the predicted stable amplitudes. We did a total of about 50 experimental runs per AC frequency, and to observe all the possible stable amplitudes.
Okay. I'd have a question to your theory. Is your theory taken from literature?
For the odd multiple period, that criteria was taken from Dobzhinsky. The quantitative theory based on equation of motion was our original work.
Okay, so what is the influence of damping on this phenomenon?
It is to make the pendulum lose momentum so that a stable amplitude can be achieved. So the solenoid feeds in momentum, and the damping takes out momentum from our pendulum. That's a balanced condition that is needed to reach stable amplitudes.
Yeah. Okay, so I have one more question for the opponent. What do you think happens for lower frequencies?
Maybe some chaotic behavior will be observed.
Okay, co chcesz jeszcze zadać? Okay, the same question for the reporter.
That's time, thank you. You move on to preparation time. The reporter and opponent can sit down.
Welcome, ladies and gentlemen. I'm Freddy Grabowski from Team Holland and I'd like to review the task number 13 shown by Singapore. So moving on, the task has three crucial parts. The first part being the power source. And so it is important to investigate the properties of the power source, like its frequency and its influence, how the frequency influences the pendulum, and the voltage we can apply, and so on. And we think that the reporter has done very good work investigating the power source. The second part are the much higher frequencies. And we think that the theory presented by the reporter was a very nice theory and it allowed him to predict many things. But his experimental research has had some big cons, which I will mention later. Then the third part are the undamped oscillations. And what we really liked here in the report was the qualitative explanation of why these undamped oscillations occur and the quantitative follow-up to these qualitative explanations. So in detail, what we really liked about the reporter's report was his theoretical model. The theoretical model, based on the model of Dobzhinsky, is a very powerful theoretical tool, and it enabled the reporter to investigate this phenomenon thoroughly. And also, what we really liked is his qualitative explanation of why this phenomenon occur and the explanation of undamped oscillations. But what we did miss in this presentation is the experiments, because in this task, there are very many important parameters. The length of the pendulum, the mass of the pendulum, the magnet orientation is very important and we didn't see any mention of it. And all these things could have been measured experimentally, and also with using such a powerful theory, it is possible to compare them with the experiments. So we really did lack all these things, especially the comparison with the experiments. So what we really liked about the opponent, therefore, is that he challenged the experiments carried out by the reporter. He asked about all the important parameters. He asked whether the initial conditions of the setup really influence the repeatability of the experiments, and therefore he challenged the experiments that the reporter called out and the comparison with the theory. But what we didn't like is that he did not refer to the theoretical model's assumptions, and he did not question whether this theoretical model will be able to predict things like lower frequencies and so forth. So in the discussion, the first part of this discussion about the damping measurement, we really liked what the opponent said, that damping may really influence this phenomenon, and asked about why the reporter used this certain method of including damping in the equations. Then the discussion moved on to chaos, and we think that chaos is really important because it challenges the experiments carried out by the reporter, and there should be more discussion of it in the presentation. And in the end, there was the induction in the coil, because the coil is not as simple as the reporter stated, in my opinion, and therefore we think there should be much more investigation in this in the presentation. So the things we'd like to see is a more experimental investigation. We'd like to see how repeatable the experiments are, vary many parameters, and see how such a powerful theory can compare with all the experiments that are possible to carry out. And also, there are parameters of the pendulum that were not investigated and we think are really important. Because, for example, the magnet on the pendulum, you can change its angle. Also, the magnetic moment of the magnet used can differ from the geometrical moment that the geometry would suggest. So such things we are able to compare with this theoretical model, but this was not done enough.
Okay, going to have to stop you there. Thank you very much. So, concluding remarks from the reporter.
Okay, now I'll present my concluding remarks as a reporter. Firstly, there is some concern over what happens at low frequency. However, I felt that the question statement clearly states that we're supposed to investigate this phenomenon at much higher frequency, and therefore my research is fully relevant to this question. And furthermore, at lower frequency, this case will simply be reduced to a conventional driven pendulum, which is already well researched and well known in the physics arena. Now also, there's a mention of possibility of chaos, but I felt that this is not really relevant to the question, and we are unable to conclude as of present whether there's chaos present. And also, for the physical nature of stable amplitudes, I did explain that this is because of the synchronization required between the AC source and the pendulum, which is an odd multiple of period. And